Hello students. Today we can see the working of electric generator in detail. An electric generator is a device which is used to convert mechanical energy into electrical energy. Its working is based on the principle of electromagnetic induction. Electromagnetic induction. It was discovered by Michael Faraday. So we'll see what is electromagnetic induction. According to electromagnetic induction, whenever there is a change in magnetic field or magnetic flux associated with a conductor or a coil, it will induce a current in it. For example, suppose we have a copper wire, insulated copper wire, and the two ends of the copper wire is fitted with a galvanometer. The galvanometer is a device which is used to test the presence of very minute current. So such a galvanometer is connected to the two ends of a insulated copper wire, and also we have a bar magnet. Suppose we have a bar magnet. They say this is the north pole and south pole of the magnet, and we know that in a magnet from north pole to south pole there will be flux lines or magnetic field lines or magnetic lines of force moving like this. When we move this magnet inside the coil, the number of field lines, or we can say magnetic flux, associated with this copper coil will keep on changing. So according to electromagnetic induction, this Faraday's principle, whenever there is a change in magnetic field associated with each turns of the coil, it will induce a current in it. According to electromagnetic induction, whenever there is a change in magnetic field associated with this coil, it will induce a current in it. We can produce change in magnetic field by moving the magnet inside the coil, or by keeping the magnet constant and steady and moving the coil up and down. So whenever there is a change or variation in magnetic field or magnetic flux associated with a coil, it will induce a current in it. And that induced current we can increase by three different methods. One, if you increase the speed of motion of the magnet, it will induce more current. If you increase the strength of the magnet, that also will induce the current. And if we increase the number of turns of the coil, that also can increase the induced current. So the induced current depends upon three factors: the speed of motion of the conductor or the magnet, the strength of the magnet, and the number of turns in the coil. And also, in which direction the current will be induced, or the induced current will flow in which direction. The direction of induced current is obtained from Fleming's right-hand rule. According to Fleming's right-hand rule, we have to stretch the three fingers of our right hand, that is the thumb, the index finger, and the middle finger, in mutually perpendicular direction, like this. Then FBI. The thumb represents the force acting on the conductor or the direction of motion of the conductor. The index finger shows the direction of magnetic field. Then the induced current direction will be given by the middle finger. Means that if the thumb is pointing towards the direction of motion of the conductor and the index finger points towards the direction of magnetic field, then the middle finger will give the direction of induced current. So we can obtain the direction of induced current by using Fleming's right-hand rule. The rule used for finding the direction of induced current is Fleming's right-hand rule. Fleming's right-hand rule. Okay, now I will show you the experiment. Here I have an insulated copper wire, a coil of insulated copper wire. The two ends of this insulated copper wire, this coil, is connected to two LEDs. The LEDs are connected, cross-connected. The plus and minus are interconnected. And this one is a strong magnet. When I move this magnet inside this coil, the magnetic field associated with these turns of the coil changes. So it will induce a current in it. By using that current, the LED will glow. You can see that. If I move this north pole of the magnet from the inside of the coil, you can see the right side LED is glowing. When I move this north pole, you can see the right side LED glowing. If I move the south pole, you can see that left side LED is glowing. Because the direction of induced current depends upon the direction of magnetic field also, according to Fleming's right-hand rule. And if I move this slowly, the LEDs are not glowing because the induced current is not enough to glow the LEDs. If I move it very fast, then only it is glowing, because if you increase the speed of motion, it will induce more current. Another example, this one is a small torch. It is working with a small generator inside. A small generator is there. It is not having any battery. A small turn of wire, insulated copper wire, a coil, and there is a field magnet also. If I move this, if I rotate the coil inside, you can see here the lights are glowing. If I increase the speed, you can see that brightness is increasing, because when we move the magnet very fast, it will induce more current. When we move the magnet very fast, it will induce more current. So we can increase the induced current in this coil by increasing the speed of motion of the conductor, by using strong magnets, and also by increasing the number of turns. So this is the basic principle of working of a generator. Now here, this one is an AC generator. This one is an AC generator. Now you can see the important parts of a generator. ABCD is the rectangular coil. It is actually an insulated copper wire. In power generator, there will be a soft iron core at the center, so that it can increase the magnetic field at the center of the coil. So by that it can increase the induced current. And also in a power generator, armature will not be rotating. Armature will be stator, and magnet will be rotating around the armature. So if either armature or magnet rotates, it will produce a change in magnetic field, and it can produce a current in the coil ABCD. The other parts of the generator, the two ends of the rectangular coil, the copper wire, is connected to two rings, a ring R1 and ring R2. These two rings R1, this end is connected over here to the ring R1, and the other end of the copper wire is connected here to the ring R2. The ring R1 is in contact with the brush B1, and ring R2 is in contact with the brush B2. These B1 and B2 brushes, they are used for drawing the current to the outer circuit. The current is produced in the rectangular coil that will flow through these two wires, and they are connected with the rings R1 and R2, and this R1 and R2 will be keep on rotating along with armature, and brushes B1 and B2 will be always pressing against the rings. It is not a permanent contact, it is always slipping. The ring R1 and R2 are called slip rings. Always when the ring rotates, the brushes will be pressing against that, and it is not a permanent fixed contact, so it will be always slipping on the brushes, so that from the rings we can take the current to the outer circuit. So the ring R1 and R2, always R1 will be in contact with the brush B1, R2 will be always in contact with the brush B2. And this is a galvanometer. It is connected to the two ends of the brushes B1 and B2 to test the current produced in the rectangular coil. and we have two field magnets, this north and south are two magnets, powerful magnets. They provide a strong magnetic field and the rectangular coil is kept inside that magnetic field. When the rectangular coil ABCD rotates in between the north and south pole, it will produce a change in magnetic field associated with the coil so that it will induce a current in it. Now we can see how this current is alternating current. How the current produced becomes alternating current. We can explain that by using a graph and a small equation. I am using this graph. In this graph, I am taking the current induced on the y-axis. The induced current is taken on the y-axis, and the angle turned by the armature or the rectangular coil, theta, is taken on the x-axis. And in the beginning, and also I am using the equation, the current I is equal to I naught into sine theta. A simple equation. Here I represents the current induced in this rectangular coil ABCD at any instant of time. This I is not a constant, it is keep on changing. It can be 0, it can reach to maximum, again come back to 0, can go to opposite side maximum. So I is keep on changing. This I naught is the maximum current that can be induced in the coil, ABCD rectangular coil. I naught is the maximum, the peak value of current that can be induced in the coil. And theta, it is the angle between the direction of magnetic field and the perpendicular or the normal drawn to the plane of the ABCD. ABCD is the rectangular coil. To the plane of the coil, if I draw a normal like this, that is an angle between that normal and this direction of magnetic field from north to south, that is theta. Right now in this diagram, if I draw normal to ABCD, that is this pen, and direction of magnetic field is north to south, so the angle right now it is 90 degree. And that angle will be keep on changing when the armature or the rectangular coil ABCD rotates. We can see that here. Suppose we imagine this is the ABCD rectangular coil, and there is a north pole here, a magnet north pole here, and south pole of the magnet here. And if I draw the normal to the plane of the coil, that is, this pen is the normal to the plane of the coil. Magnetic field north is here, south is here. So the direction of magnetic field is from north to south this way, and normal to the coil also in the same direction. So both are in the same direction. So the angle theta equal to 0. So at this orientation of the armature, angle theta equal to 0. We know that if theta equal to 0, sine 0 is equal to 0, then the current induced I will be equal to 0. Means right now at this portion of the armature, the current induced in the rectangular coil or armature will be 0. Means on this graph we are at this position, the current is 0. Now suppose the armature or the rectangular coil start rotating. When it rotates this direction, okay, the current will keep on increasing because theta is increasing and sine value increasing, and we know that the sine theta value is maximum when sine theta equal to 90 degree, sine 90 equal to 1. So when the armature rotates 90 degree, theta becomes 90 degree, then sine 90 value is 1, sine 90 is equal to 1, then I become equal to I naught. Means the current become maximum, the peak value. Means the current will start increasing when the rectangular coil rotates, the current start increasing from 0 to a maximum value. When the angle theta become 90 degree, current reaches a maximum. This maximum current we can show on the y-axis, that is I naught, the peak value of current. This is happening in the first quarter of the rotation, means 90 degree. Again the armature or the rectangular coil is keep on rotating in the same direction. Now again it rotated another 90 degree, so the total angle rotated is 180 degree. When the angle become 180 degree, that is theta is equal to 180 degree, sine 180 degree is again equal to 0, then current induced become 0. Means we can see that as the rectangular coil rotates, current again decreases to 0 when it completes another 90-degree rotation, means total 180-degree rotation. So it started from here 0 degree, means angle between the direction of magnetic field and direction of normal drawn to the plane of the coil, 0 degree. It increased to maximum when 90 degree, again decreases to 0 when 180-degree rotation, and this is the first half of the rotation. So in the first half of the rotation, initially current increases from 0 to maximum in first 90-degree rotation. Again, on completion of the first half of rotation, current reaches back to 0. Now it is rotating downward direction, another 90 degree. So total angle turn is 270 degree, and we know that theta equal to 270 degree, theta is equal to 270 degree, and sine 270 degree, sine 270 degree is minus 1. So in this equation, I equal to I naught into sine theta is minus 1, so the current become equal to minus I naught. So current minus I naught means it is in the negative direction, means current come to negative maximum at this position where theta is equal to 270 degree. The current become negative maximum in the negative direction maximum, that is minus I naught. Current goes to reverse direction. Now the last quarter of rotation is remaining. It started from here, 0 current, 90 degree maximum current, 180 degree, it becomes again 0, 270 degree, current become minus I naught, reverse direction maximum. Again it is rotating, completing on full rotation 360 degree, current come back to 0, because when theta equal to 360 degree, sine 360 is equal to 0, so I is equal to I naught into 0, that is equal to 0. Means the current induced will come back to 0. This is called one cycle of AC. And how many cycles like this is produced in 1 second, that is called frequency of AC. And in India, AC is produced at a frequency of 50 Hz. It means when the armature coil of the power generator, it rotates 50 times in 1 second. In one half rotation, the current will be flowing in positive direction. The next half rotation, the current will be flowing in the negative direction. So in one full cycle, half current will be flowing positive and half cycle will be flowing negative direction. So in a full cycle, 2 times the direction of current will change. Means if the positive half cycle, if the current is flowing towards right side through a wire, and the negative half cycle, the current will be flowing towards the left direction through the wire. So in 1 second, 2 times direction will change. So in India, the AC is produced with a frequency of 50 Hz, is the armature of the power generator will be rotating 50 times in 1 second. So 50 times current will flow in right direction and 50 times towards left direction, means total in 1 second 100 times the direction of current will change. And such a current which changes its direction periodically is called alternating current. So in the armature of a generator, the current produced is always alternating current. Now we can see how the direction of current changes from the rotation of the rectangular coil itself. Suppose this is the rectangular coil and this side is the side AB and this is the side CD. The side AB is connected through this wire to the ring R1 and the side CD is connected through this wire to the ring R2 and to the brush B2. Suppose the armature or the rectangular coil is rotated this direction. So the side AB is coming out of the board and the side CD is going into the board if it is rotated this way. So when the side AB is moving out of the board, if I apply Fleming's right hand rule, the direction of magnetic field is from north to south, that is by the index finger, and the side AB is moving out of the board, that is the thumb is showing the direction of motion of the conductor. So if I show the direction of magnetic field by the index finger and direction of motion of AB towards this direction by the thumb, and we can see the middle finger, it is showing the direction of current, means at the side AB the current is flowing in the upward direction. At the same time, at the side CD is moving into the board, but the magnetic field is in the same direction, north to south, and direction of motion of the conductor CD is into the board. So we can see the middle finger, it is downward direction, means at the side CD current is flowing in the downward direction. Means in the first half rotation we can see through this rectangular coil current will be flowing in the direction ABCD. In that time, suppose the current flowing through the side AB, it is flowing upward, so the ring R1 in which the current is flowing in the upward direction, suppose I am taking ring R1 positive. So the ring R1 is in contact with the brush B1 also. So in the brush B1 we will be getting a positive current. So brush B1 is positive, current will be flowing in this direction. And the side CD, current is flowing downward direction. So that side CD is connected with the ring R2. So I am taking the downward direction of current as negative. So the brush B2 I can take negative. So ring R2 is negative and the brush B2 also negative, and the current is flowing downward direction. So we can see here in the external circuit from positive to negative, the ring R2 is negative, ring R1 is positive. So brush B1 is positive and brush B2 is negative. So the current is flowing in this direction in the external circuit. This is happening in the first half rotation. The second half rotation, the side AB will reach here and CD will come to here. But the side AB when reaches here, ring R1 is still in contact with B1. So when the side AB reaches here, the current will be flowing in the downward direction. Means when the current flows downward direction, ring R1 become negative. And the side CD reaches here, the ring R2 become positive, because the side when it reaches, the CD when it reaches here, it will be moving upward direction, so it will be positive upward current, and the side CD will be, AB will be moving into the board, so the current will be in the downward direction. So in the second half rotation, ring R1 become negative and ring R2 become positive. When ring R1 become negative, in the brush B1, we will not be getting positive current, we will be getting negative current. And when the ring R2 become positive, brush B2 also will be positive. So in the direction of current, the second half cycle will reverse itself, means it will be flowing from positive to negative, means in this direction. So the direction of current reverse in the second half rotation, because the brushes B1 and B2 are always in contact with the rings R1 and R2, but the rings R1 and R2 are becoming plus and minus, they are changing the polarity in each half rotation. So externally we will be getting a current which changes its direction in each half rotation. Such a current which changes its rotation, which changes its direction periodically is called an alternating current. Now in a DC generator there is a small difference only at this area, means at the rings R1 and R2. In a DC generator, only the difference is that these two slip rings will be replaced by two split rings, or it is called a split ring commutator. The two ends of the armature will be connected to two half rings like this. That is ring R1, it is in contact with the brush B1, and ring R2 is in contact with the brush B2. So here the brush B2. Now what is happening in DC generator? We can see only the difference is here only. The slip rings are changed by split rings. It is called split rings, or it is called split ring commutator. So what is happening here? The first half rotation, ring R1 is in contact with B1 and ring R2 is in contact with B2. And in first half rotation, ring R1 was positive, so brush B1 also is positive. Ring R2 is negative, so brush B2 is negative. At the end of the first half rotation, ring R1 will go to brush B2 and R2 will come to brush B1. And we know that in the second half rotation, when CD reaches here, ring R2 become positive. So when the second half rotation, the ring R2 will reaches to B1, and when ring R2 reaches to B1, current will be flowing upward direction, so R2 become positive, and still in the external circuit through the brush B1 will be getting positive current here. and the ring R1 will reach here, means AB reaches here, ring R1 also will reach this side. So when the ring R1 reaches this side, it becomes negative because current will be flowing downward direction. So in the brush B2, still we are getting negative current. Means in the armature or the rectangular coil of DC generator, now it is a DC generator, the rectangular coil ABCD of a DC generator, it is producing AC itself, alternating current itself, but externally it is converted into DC because of the interchanging of the rings R1 and R2. In AC generator, the full rings, the slip rings R1, the slip ring R1 is always in contact with the B1 and R2 is always in contact with the B2. But here the split rings R1 and R2, they are interchanging their position between brushes B1 and B2 in each half rotations. So what is happening inside the rectangular coil, in one half rotation the direction of current changes. So externally the ring R1, R2, they also changes the direction of current. So if two times if we change the direction of current, it becomes the same direction. For example, in first half rotation I am changing the direction of this pen like this, and since the rings are also interchanging, that also will change the direction once again, so it becomes straight in the same direction. So if two times if we change the direction become the previous one itself. That is what happening in the external circuit. In the first half rotation, direction of current will change in ABCD into DC, BA, and ring also interchange their position. So the external circuit always B1 will give positive, B2 will give negative. So if we are drawing that graph, the graph of the DC current available in the external circuit, that DC graph will be like this. It will be like this. So this DC direct current, it is not just like the DC from a battery, it is called a pulsating DC. When the armature is, the normal to the armature is parallel to the magnetic field, current is 0, it will go to maximum 90 degree, 180 0, again it will go to maximum and 0. So this current is increasing and decreasing between the maximum and 0 according to the theta, the angle turned by the armature coil. And such a DC is called pulsating DC. If we are drawing DC of a battery, it will be always flowing steady in the same magnitude without any change. But here the value magnitude is keep on changing, but it is always flowing only in positive direction, not in negative direction. So it is called direct current because it is flowing only in one direction, but its magnitude is keep on changing. So it is called a pulsating DC. It is not just like the normal DC getting from battery. A DC getting from a battery will be a straight line without changing magnitude. It will be a steady current. So such a current which always flow only in one direction without changing the direction, such a current is called direct current, and the current which keep on changing the direction to plus and minus is called alternating current. Now you can see the demo of this working of the generator. Okay, this is the generator. It consists of an armature. This is the armature. It is insulated copper wire wound on a soft iron core. It can rotate between the magnets, and this soft iron core of the armature is fitted with an axle also. This is the axle. The other side of the axle you can see here, and this axle can be rotated by using this wheel. It is connected through the belt here, and the armature, when it rotates, the axle also rotates, and the axle is also fitted with the two rings here. This is the rings. You can see these rings are not touching each other. Two rings are there. Okay. These are two slip rings, and the slip rings are in contact with the two brushes. This one brush, the other brush is at the bottom. This is the second brush. One brush is in contact with the first half, one ring. The bottom brush is in contact with this half of the ring. Two rings R1, R2, brush B1 and B2. And this is the field magnet. Field magnet, if I remove, okay. This red part is the north pole, blue part is the south pole, and you can see the axial and the insulated copper wire is the soft iron core on which insulated copper wire is wound. You can see here this soft iron core is not a thick metal, it is a laminated thin sheet of soft iron to reduce the eddy current. This is laminated soft iron core on which the insulated copper wire is wound, and it is kept between two magnets, strong magnets, north pole and south pole. And when we rotate the armature between the magnets like this, it will produce electric current. By using that electric current, we can glow these two bulbs. Okay, this is an AC generator. It is having two slip rings. Instead of these two full rings, if it is split, that will be a DC generator. You can see here when the armature rotates between the magnets, the bulb is glowing. Okay, there are two bulbs glowing. If I increase the speed, you can see the speed increases, the brightness of the bulb is increasing because more current is induced due to the large change in magnetic field.